Hey, hi everybody. This is the first video I'm doing for calculus class, and so we're doing how we find Taylor polynomials, and that was a section I had you guys read up and all, but I'm not sure if I gave you assignments on this, but um, so here the idea is we're going to kind of first approximate functions that are not polynomials by using polynomials. So here we go. We have the function f of x equals e to the x, and find the first degree polynomial whose slope and value f at x equals 0. So that would mean in this case that f of 0, oops, put the pen on, pen, okay. So that means f of 0 is e to the 0, which is equal to 1. And then we want to find in this case f prime of x, which is equal to e to the x, and therefore f prime of 0 is equal to e to the 0, which is equal to 1. So first degree polynomial, that's a linear function. That's a linear polynomial, and so what comes down to is that we have just a linear approximation we know is going to be our slope is 1. And we have in this case of a coordinate of 0, 1. Well, hey, our polynomial we'll call in this case would be y is equal to 1x plus 1. Okay, all right, so that's not a big deal. All right, so let's move on to our next degree of our second degree polynomial. So we get the this linear approximation, this line. It's not so great of approximation because of the fact that when you start moving away from 0, it's not that accurate to approximate e to the x. So let's find the second degree polynomial. Okay, so we'll call it p2. The first one was p1. So p2, where p2 of 0, the second polynomial at 0 is the same value of the function f of 0, which we know is equal to. So we know that p2 of 0 was equal to 1. And we know that p2 prime of 0 has to equal to f prime of 0, right? p2 prime of 0 equals f prime of 0, but f prime of 0 was also equal to 1, okay? And then, of course, now let's take a look at our second derivative. Well, f double prime of x is equal to, well, derivative of e to the x is just e to the x. And so therefore, the second derivative of this function is going to be at 0, also 1. So now we're going to work this out. Well, we know here, okay, we know in this case that p2 prime is equal to the integral of p2 double prime of x dx, so of x dx. And so we know in this case that, well, that's just equal to, well, 1. So 1x plus c. All right, so p2 prime at 0 is equal to 1 times 0 plus c, and that's equal to 1. Remember, it's 1 here. So that means c equals 1. Therefore, p2 prime of x is equal to 1x plus 1. Okay, so now we want to find the function of p2 of x. So p2 of x is equal to the integral of p2 prime of x dx. And so the integral of 1x plus 1 is going to be x plus 1 over 2x squared plus c. And so again, we know in this case that at p2 of x, p2 of 0 actually, is equal to, in this case, 0 plus 1/2 of 0 plus c, which is equal to 1. Therefore, we are going to get p2 of x at 0 is equal to 1 plus x plus 1/2 x squared. Okay, so that's not so bad. All right, so we see we just take the integrals, right? And then let's do the third one. All right, so now let's do the third one. Okay, so again, the idea is that P3 of 0 should equal to f of 0. Okay, p3 prime of 0 should equal to f prime of 0. p3 double prime of 0 should equal to f double prime of 0. And p3 triple prime of 0 should equal to f triple prime of 0. And so again, we're going to find out that all these equal to 1. And so it's almost like working backwards. You almost can, we see in this case that, we can go through the whole process, but we're going to end up with, we know that we're going to start, again, very similar to before, P3 double prime of x is going to equal to, we know is going to be 1 plus x. P3 prime of x is going to equal to 1 plus x plus 1 over 2x squared. And so we'll notice a pattern here that P3 of x will equal to the integral of this, which should be in this case, and essentially the same thing, where c equals 1, we're going to get 1 plus x plus 1/2 x squared plus 1 over 6x cubed. Okay, now what happens is this, we see the 1 and the 1/2 and the 1/6, they're not random. Okay, the 1/6 really is, 1/6 really is 2 times 3, which in this case is same thing as, well, times 1 is going to be 1 over 3 factorial. And then the 1 over 2 is same as 1 over 2 times 1, which is equal to 1 over 2 factorial. Now, I mention this because of the fact that, we'll see that we keep expanding with the same thing, we should get, the same way, instead of writing it out in this manner. So P3 of x is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third plus, if I want to go further, all right, let's say, for example, I'll go 4, P4, that'd be 1 over 4 factorial x to the fourth, and so on and so forth. And so we can see this pattern developing, okay? And so we see here that if we expand all out, we will find that, the nth p, in this case, the nth term, nth polynomial of x will be 1 plus x plus 1 over 2 x squared plus 1 over 3 factorial x cubed plus dot 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 all the way to 1 over n factorial xn. This means we can approximate the function f of x equals e of x by using a polynomial that will be in the form of the above. The further we go along, the better approximation. So on your graphic calculators, you should type in the following. Not this, y equals. Oh, okay, so I cleared everything here. So, okay, so we're going to do, in this case, e to the x. All right, so second e to the x. Okay, oops, x here. Let me delete this part, oops. Okay, and then what we're going to do is we're going to plug in the each one. So it was the next one was 1 plus, so it was in this case 1 plus x. So we have 1 plus x. Okay, and then we're going down. And then we're going to type in, so the next one was 1 plus x plus 1 over 2 x squared. Okay, the next one will be 1 plus x plus 1 over 2 x squared plus 1 over 6 x to the third. Remember, not 3, but 3 factorial. Okay, and we'll go in one more. All right, we'll go 1 plus x plus 1 over 2 x squared. Oops. Delete this. X squared plus 1 over 6 x to the fourth. X to the third, actually, x to the third. X to the third plus 1 over, now 4 factorial is 24. x to the fourth. All right, so we're going to take a look at the graph. Hopefully we'll graph all these. Okay. And you'll see in this case that as the line, of course, the original graph is going to be, if you can notice, is in blue, and so we can turn off some of these here. So we can turn off some of these so that okay. So we can maybe do each one separately. So I'll add them on as we go along. So you can turn off the graphs by just going downwards and each one hitting enter on the equal sign so that the equation is still there, but we'll graph them as we go along. So our first graph will be here. That's our first graph, okay? So notice at x equals 0 is going to be pretty good approximation. Actually, so that's okay. Now let's come on and do the, okay, include the y3, enter that in, and graph. And so this actually hugs the graph a little better for the original blue. Okay, now let's go back to here and we're going to, let's go to our third polynomial, enter, and then graph. And so you'll see in this case, it actually gets closer, again, not all the way across, but a little further out from 0 is a better approximation. And we'll see here for the last one. Okay, and we'll graph here. And so notice that it gets further along, and I'm gonna actually just turn off the other graph so you can see a little better. All right, you can do that too if you want to. I'll just turn this off and then turn this off. And so that the further out one, in this case, the fourth polynomial is very close to. Now, notice not here, but notice as we get further away from 0, it is pretty darn close to the graph itself. And the better approximations will occur when we are going to go further out, okay? And so again, we can approximate non-polynomial functions in a polynomial form and get better and better approximations the further we go along. We use c equal the value of 0 to center about our function f of x equals e to the x. Let's use an arbitrary value of c expand to the nth term.